So this is one last concept that we are left with. Let's start with mutually exclusive events and try to understand what they are first. Mutually exclusive events. All right, so this is a terminology that you need to know in probability. And this basically is about two events which cannot happen at the same time. Let me start with an example. Let's say you've got two events like this. Event A is, let's say that the minimum temperature today in Lahore is, let's say, 10 degrees Celsius. Okay. Event B is, it is, or let's say there is snowfall in Lahore today. Okay, Lahore in Lahore doesn't have snowfall in any case. So let's choose a different city. Let's say we have Murray here. Okay. The minimum temperature today in a particular city, let's say Murray here, is 10 degrees Celsius. And we say there is snowfall in Murray today. These are two events. Now, if the minimum temperature is 10 degrees Celsius, there is no probability of snowfall. And if there's snowfall in Murray today, then the minimum temperature cannot be 10 degrees Celsius. So these two things cannot happen at the same time. All right. So what we say about these two events is that they are mutually exclusive. If one event happens, the other cannot happen. All right. So that's how we explain this. We say, if one event happens, if event A happens, B cannot happen. All right. The probability of that becomes 0. And similarly, if event B happens, then A cannot happen. Essentially, the two events A and B cannot happen together. That is what mutually exclusive events mean. All right, so you've got two events that cannot happen together. All right. Now, if you were to think about this and draw a tree diagram, draw a Venn diagram for this, not a tree diagram, what would these events look like on a Venn diagram? So if you have one circle for A, this is event A, let's say. All right. And you've got another circle here. And this is event B. Then if they're mutually exclusive, there's going to be nothing in common between them. Because you know, if you are in circle A, then you cannot be in B. And if you are in circle B, you cannot be in circle A. There's nothing in common between them. So in set notation, what we say is the probability of A intersection B is equal to 0. This probability is going to be equal to 0. All right. Now, this is what it looks like. This is the condition that you've got for mutually exclusive events. All right. So if two events are mutually exclusive, this condition has to be true. So this is true for mutually exclusive events. What exactly does it mean? In words, it means the probability of A and B happening together at the same time. You can say the probability of events A and B both happening at the same time. Both happening at the same time. This probability is equal to 0. All right. They cannot happen at the same time. All right. So their intersection is equal to 0. This is what mutually exclusive events are. All right. So this is what we've got for mutually exclusive events. If one event happens, the other cannot happen. And that means in mathematical terms that the probability of A intersection B is equal to 0. Okay, so whenever you have to prove that two events are mutually exclusive, what you do is you find the probability of their intersection. That means probability of both of those events happening at the same time. You find that if that turns out to be 0, that means that those two events are mutually exclusive. All right. Now let's take another example. In fact, let's talk about the other case now. The other type of events, which are independent events. Let's think about this now. Let's see what they are. Independent events. Now, not the same. Mutually exclusive does not mean the same thing as independent. In fact, if one of them is true, the other cannot be true. So if events are, if two events are, so that was not a very precise statement, but if two events are mutually exclusive, then they cannot be independent. Okay, so there's actually a relationship between them as well. We'll talk about that in some time. But let's think about independent events. So I'm missing an N here. That looks weird. Independent events. All right. Now, what are independent events? Independent events mean that if there are two events and if they're independent, then the probability of one event happening does not affect the other event. Okay. Or in other words, if two events are independent, if one event happens, it does not impact the probability of the other event happening. Okay. If that is true, then those two events are independent events. Now, let's take an example for this as well. So we were talking about weather earlier, snowfall and temperature. Let's talk about that. So let's say we have two events. One event is A. We say the minimum temperature in Lahore is 10 degrees Celsius today. And there's another event, that's event B. There is snowfall in what city? Let's say in Toronto today. There's snowfall in Toronto today. Now, these are totally unrelated from each other to each other, right? So whatever the temperature in Lahore is, it doesn't really affect there being a snowfall in Toronto. All right. And whether there's snowfall in Toronto or not, it does not have any impact on the temperature in Lahore. Maybe in the grand scheme of things, there's some minute impact, but it's going to be very negligible. Okay. So there is no impact of these events on each other. So we say they are independent events. Okay. They do not have any impact on each other, each other's probability. Now, let me write that down as well. So what this means is if event A happens, it does not have any impact. So it does not affect the probability of event B happening as well. Okay. And also the other way around. So if event B happens and then that does not have any impact on the probability of event A happening. Okay. So it's true both ways because they're independent of each other. So event B happens, it does not have any impact on the probability of event A happening. So they do not impact each other, right? Now, what does that mean? That means if we had probability of A given B, for instance, if we were looking for a probability of A given B, if we were finding the probability of event A given that B is true, it would just be equal to probability of A. Why? Because it doesn't really matter whether B happened or not. So if you're looking for the probability of A given that B happens, it's still probability of A because B does not have any impact on A. So it stays the same as before. Whatever it was initially, whether B happens or not, it stays probability of A. Okay, it does not change. Similarly, probability of B given A, that is also just the same as probability B. It does not change at all. Okay, so if event A happens, it does not have any impact on B, and the probability of B remains the same as whatever it was before. All right. Now, from this, we actually get a very important result that you use to figure out whether two events are independent or not. Let me write that down here. It comes from the condition probability formula. Remember the condition probability formula? It looks like this: probability of A given B, that equals probability of A intersection B divided by probability of B. That's what the conditional probability formula looks like. If I were to rearrange this formula, it would be probability of A intersection B equal to probability of A given B multiplied by probability of B. That's what this formula would look like. All right. Now, if events A and B were independent, what would happen in that case? If A and B are independent, then we know this probability is going to be just equal to probability of A, right? Because probability of A given B is just the same as probability of A. It does not change at all. So in that case, this actually translates to probability of A intersection B equal to probability of A into probability of B. And that is the condition that we've got for independent events. Whenever we need to prove that two events are independent, what we'll do is we'll be using this relationship. We'll see whether the probability of the intersection, the probability of both A and B happening at the same time, whether that's equal to the product of the probabilities of A and B happening separately. All right, their overall probabilities of happening. If their product was equal to the probability of their intersection, in that case, the events would be independent. So this is going to be true for independent events. Whenever two events are independent, this equation should hold. If this is not, if this equation is not true, then it would mean the events are not independent. All right. So these are the two results that we need to remember now. So this is the result that we have for independent events now. The first one was for mutually exclusive events. If two events are mutually exclusive, probability of A intersection B equals 0. If two events are independent, probability of A intersection B equals probability of A multiplied by probability of B. So these are the two relationships, two rules that we use to figure out whether two events are independent or not. All right. Any quick questions on this now? So these are two concepts that we've done now. Mutually exclusive events, independent events, they're not the same. They have different meanings. And we have discussed what each of them means now. Any questions, anyone? No? Is that all right for everyone? Okay. Now let's discuss another example. So all of you would be familiar with those examples in O levels where we used to have some container, and that container used to have some balls in it, and you would take out one ball after another. Remember that? So let's take one of those examples because that's actually a good example of independent and non-independent events. Let's say we've got a container like this. And this container has some balls in it. Let's say you've got some blue balls here. Let's say you've got 8 blue balls in it. And you've got some red balls. Let's say you've got, I don't know, 15 red balls in it. Okay. Now you need to find the probability. Find the probability let me actually explain the scenario first. You take out 2 balls from this container, let's say. Let's say you take 2 balls out from this container. Find the probability of getting two red balls. Find the probability of getting 2 red balls. This is what we need to find. Okay. Now, how do we do this?
With replacement or without replacement?
That's a good question. So it doesn't really say whether it's with replacement or without replacement. Now, whenever it does not mention whether it's going to be with replacement or without replacement, since you're taking two balls out, the most logical explanation for that would be that you are not replacing them back, because it doesn't say anything like that in the question statement. So whenever you are not specified whether you're taking out something or doing something with replacement or without replacement, you always assume it's without replacement. Okay, so you're taking out one ball, you're not putting it back, you're taking out another ball after that. Okay, if it was with replacement, they would always specify that in the question. Okay, so if it's with replacement, it's always specified. Otherwise, if it doesn't say anything, you always assume it's without replacement. Okay, so this is without replacement. Now, what's the probability of getting 2 red balls? Now, probability of getting a red ball the first time, that's 15 out of 23. Right? There are 23 balls in total. Out of them, 15 are red. So getting the first red ball, the probability for that would be 15 over 23. Now, given that you have a red ball the first time, what is the probability of getting a red ball the second time? That will be reduced to 14 over 22. All right. Because the number of red balls has reduced by 1 and also the total number has reduced by 1. So taking a red ball the second time would be 14 out of 22. The probability for that would be 14 over 22. All right, so this is what you end up getting from this. Now think about this. Are these two events independent? Probability of getting a red ball the first time and probability of getting a red ball the second time. They're not independent. Why? Because what happens the first time has an impact on what happens the second time. So if you take a red ball the first time, then the probability of having a second red ball changes. It's 14 over 22. If you have a blue ball the first time, the probability of getting a red ball the second time would have been 15 out of 22 because there would still be 15 balls in that case, 15 red balls in that case. All right. So what happens the first time has an impact on what happens the second time. So whenever you've got a situation where you are doing something without replacement, these probabilities that you get are not going to be independent. Okay. But if I were to change this a bit, if I were to change the statement and instead have something like this, so it's exactly the same thing, but we add another condition here. So we say, let's say you take 2 balls out from the container, but this time it's with replacement. So now it's specified. It's with replacement. That means when you take out one ball, you put it back, then you take out another ball after that. Now, what about the probability of getting 2 red balls in this case? Now, the total number of red balls is 15 out of 23. So the probability of taking out a red ball the first time is 15 over 23. What about the second time? That is still second time is still 15 over 23 because once you've taken out a red ball or a white ball, whatever the first one was, okay, so let me repeat. I don't know why people do this, but let's look at this again. Let's say you take 2 balls out from the container with replacement. Find the probability of getting 2 red balls. Now, this time we're doing it with replacement, right? So we're taking out one ball and then putting it back and then taking another ball out from that container. What's the probability of getting a red ball? The first time, it's 15 over 23. But the probability of taking a red ball the second time, taking out a red ball the second time remains the same this time because the total number of balls is still the same. And the number of red balls is also the same. So the probabilities are repeated here. Okay. So this is what you get in this case, 15 over 23 into 15 over 23. Now, in this case, what happens the first time does not have any impact on what happens the second time. All right. So these events are independent. Okay. Now it doesn't matter if you took out a red ball the first time or a blue ball the first time. It does not have any impact on the probability of taking out a red ball the second time. All right. So from this, we understand whenever we've got a situation where we do something with replacement, the events that we get from that, they're going to be independent events. And if we do it without replacement, we're not putting what we took out the first time, we're not putting it back, then the events are not independent because they are affecting each other. What happens the first time is having an impact on what happens the second time. All right. So this is another thing that you need to remember, keep in mind. Whenever something happens with replacement, they're independent events. And if it happens without replacement, they're not independent. All right. Is that okay to everyone? Any problems with this? Because now we can do some practice questions in this. That's it. That's it about these two types of events, independent and mutually exclusive events. That completes all our probability concepts as well. So now we should be able to do all questions from the worksheet. All right. Now let's start with a couple of questions from that worksheet. I expect you to have done some practice by now at least, so you can also let me know if you have any specific problems. We'll spend tomorrow on only doing some more practice questions. And then the day after tomorrow, we'll be starting permutations and combinations, inshallah. Probability worksheet. Okay. Let's do this. This is question number 12 from the worksheet. Let's have a look at this because this has both of those types of events, independent and mutually exclusive. Let's try to do this. This is question number 12 from the worksheet. All right, so we've got two fair 12-sided dice with sides marked 1, 2, 3, 4, 5, 6, and up to 12. These dice are thrown, and the numbers on the sides which land face down are noted. Events Q and R are defined as follows. This is event Q and this is event R. We need to find the probability of Q first and then the probability of R. Now let's think about this. We've got 12 numbers here. Event Q is that the product of the two numbers that we get is 24. So we're rolling two dice and they have numbers written from 1 to 12 on each of them. What's the probability that the product turns out to be 24? Now we could think about drawing a two-dimensional table for this, but how many entries is that going to have? It's going to have 12 on one side, 12 on the other side. 12 times 12, that's 144 values that you would have to input input in that table, right? So we can't do that. That is not going to work because it's going to be too time consuming. So what do we do instead? We just think about it logically. It says the product of the two numbers is 24. So we think about two numbers out of these 12 numbers where the product is equal to 24. Okay. So you think about the factors of 24, 1 and 24. Well, we can't have that because the greatest number that we got here is 12. We could have 2 and 12. Let's start from that. We could have 2 on the first dice and 12 on the second dice. That's one possibility. And also the other way around then. 12 on the first, 2 on the second. The second case would be 3 and 8. That gives us product of 24. And the other way around, that's 8 and 3. What else could we use? 4 and 6. That also works. 4 on the first dice, 6 on the second, or the other way around. And these are the 6 possibilities that we've got. Okay, these are the 6 possibilities that we get from this. Now, what about probability? How do you find probability? The number of favorable outcomes. There are 6 possible outcomes. Out of how many? Got 144 total outcomes, right? 12 on the first dice, 12 on the second. The total number of possible outcomes becomes 144, right? Because you've got, if the first dice has 1, the second dice can have 1, 2, 3, 4, 5, 6, up to 12. There are 12 possibilities there. If this first dice is 2, the second has options of 1, 2, 3, up to 12. Similarly, for 3 on the first dice, 4 on the first dice, 5 on the first dice, you've got 12 into 12, 144 possible outcomes. So if you write probability of Q here, that is going to be 6. That's the number of cases we've got here, over 144. And that turns out to be 1 over 24. This is the probability of event Q. Okay. Now, let's look at the second one. Now it says find the probability of R. Okay, find the probability of R. What's event R? Event R is that both of the numbers are greater than 8. So we are throwing 2 dice. Both the numbers that we get on the dice are greater than 8. Find the probability of that. Now, what could our options be in that case? Both numbers have to be greater than 8. So 8 is not included, remember. So one possibility is that the first number is 9 and the second number is 9. And then we could have more possibilities with 9 on the first dice. And then you could have 10 on the second, 9, 11, 9, 12. Similarly, you could have 10 on the first dice and then 9 on the second. You have 10, 10, 10, 11, and 10 and 12, and so on. You got 4 possibilities with 11, and you got 4 possibilities with 12. How many cases do we get in total? These are 16 cases. 16 out of how many? Out of 144. So the probability of R therefore becomes, 16 out of 144. And that gives you 1 over 9. This is the probability of event R here. Okay, that's the second part. Event R was that both of the numbers are greater than 8. So these are all possible outcomes for that out of 144. So the probability turns out to be 1 over 9. 16 over 44, that's basically 16 over 144, which is 1 over 9. Okay, let's look at the next part now. Now in the next part, it says, are events Q and R exclusive? That means, are they mutually exclusive? How do you figure that out? Remember the condition? The condition was, if 2 events are mutually exclusive, the probability of their intersection should be 0. All right, that's what we did here. For mutually exclusive events, if you want to prove that 2 events are mutually exclusive, the probability of the intersection should be 0. So that's what we need to prove if they're mutually exclusive. Now let's think about this. We've got events Q and R. Is there anything in common between them? Look at these outcomes and look at these outcomes. There's no common outcome. There's no outcome that's appearing in both of them. All right, because If you've got two numbers that have a product of 24, then they both can't be greater than 8. That's not possible because then you get a bigger number. And similarly, the other way around, if both numbers are greater than 8, then you cannot have a product that is 24. So there's nothing in common. You can see in the outcomes as well, there's nothing in common. So what do you say then? You say probability of Q intersection R equals 0. There's no intersection. They've asked you to justify your answer. So you have to give a reason for that, right? So this is the reason. Probability of Q intersection R is 0. That means that Q and R are mutually exclusive. These are mutually exclusive events. All right, let's look at part 4 now. Now part 4 says, are events Q and R independent? Now, how do you figure out whether two events are independent or not? This is the condition that we've got for that. If two events are independent, probability of A intersection B, that should be equal to probability of A multiplied by probability of B. This is what you need to check for. So what we need here is we need probability of Q intersection R, and we need to figure out whether that's equal to probability of Q into probability of R. Now we've already found the probability of the intersection, that is 0. Probability of Q, that is 1 over 24. And probability of R, which is 1 over 9. Now, of course, these are both non-zero numbers. They cannot be equal to 0. 1 over 24 into 1 over 9, that is going to give you 1 over 216. So you say these are not equal. Probability of Q intersection R is not equal to the probability of Q times probability of R. Since these things are not equal, that means Q and R are not independent because this condition is not met here. They are not independent. Okay. And this is actually something that's true for all mutually exclusive events. Whenever you've got two events which are mutually exclusive, they cannot be independent. Why? Because the intersection will always be 0 in that case. If the intersection is 0, you'll have some probabilities on the right side at least. Okay, so their product is not going to be equal to 0. You can also think of it this way. Look at these Venn diagrams. These are mutually exclusive events. What that means is, if you know that A happens, then B cannot happen. If A happens, the probability of B becomes 0. And similarly, if event B happens, the probability of A becomes 0. So they are having an impact on the probability of the other event happening, because if one happens, the other cannot happen. So it is affecting the probability of the other. If you're in one circle, you cannot be in the other circle. All right, so there is an impact. So whenever you've got exclusive events, since they have an impact on each other, that means they cannot be independent. Okay, so you can actually write that down here as well. At the end, if two events are mutually exclusive, they cannot be independent. Okay, that's not possible because they are affecting the probability of the other happening in that case. That means they're not independent. All right. Although you should still use this reasoning in any case, you should try to think about this, whether this turns out to be equal or not. And for mutually exclusive events, you should check for whether the intersection is 0 or not. But keep in mind, if you're getting this as mutually exclusive, then you should be getting not independent here as your final answer. Otherwise, you're doing something wrong. All right. So that's how you prove whether something is mutually exclusive or independent.